In the previous video clip, we find the beta head that having some optimization gap so that we can prevent or improve the generalization error. But in many cases, we also face some suboptimal issue which is critical for training itself. Okay, so when this is very huge, then the training error itself is very bad. When your network is not trained, then although there is a very tiny generalization gap, almost no overfitting, because training itself pretty bad, your validation error also very bad. This is not what we really want. Okay, so for this case, we have to find out better beta head that having less optimization gap. Okay, actually optimize the neural network loss function is very difficult. First of all, the neural network usually have very complicated structure, so it is very hard to understand the loss function landscape. So it is very difficult to design some algorithm without gradients. So almost every optimization technique for your neural network is based on the gradient and backpropagation. Okay, and also the loss function is not convex and it has many local minima. So the three things, we have to use gradient, but the loss function is not convex, and the loss function has many local minima, which make your optimization extremely difficult. Okay, imagine the parameter is just single, so the input parameter is just one variable. Then you can draw some loss function, and let's say the loss function looks like this. Okay, so this is the x-axis represent the beta, and the y-axis represent the loss value. This loss function shape is very difficult to find the real optimal point here using simple gradient descent. Why? First of all, the initial point is very important. Imagine when you start from here, then your gradient will be almost zero. Gradient is almost zero means you will have almost zero movement for a while. So you have to wait a huge amount of time to observe some tiny decrease of loss value. Okay, which means in your optimization process, you will stuck and you never escape this area. So in the end, your solution will be pretty bad. When you start from here, then this is good at the beginning because you have a very deep decrease part, so you can see very nice improvement at every step. But in the end, it will stuck at here, and which has some gap with the true optimization point. Okay, and One sad thing and one very bad part for deep learning training is if you don't carefully choose the initial point, most of cases the initial point will locate this kind of area. You will observe almost zero gradient and you will observe almost zero decrease on your loss value. So for millions or billions of iteration, your loss value will remain the same and you stuck there and your algorithm never trained and your error, training error will be very bad. So validation test error as well. So to solve this issue, deep learning engineers invent some nice initialization techniques so that with very high probability the initial point located in some nice area. Okay, so that's why initialization is very important in training your neural network. Okay, and the second issue when you train your neural network is so when you draw some contour of your loss function, the shape is very ugly and very sharp area and very wide area and so on. So this is contour of your neural network loss function. It looks like this. And this is very bad when you use gradient-based algorithm. When there are some sharp axes and very wide valley for some axes. So for instance, in this case, this is very sharp to the vertical, but very wide for this horizontal line. Then with simple gradient descent rule, you will see a huge oscillation for this direction. And the convergence speed with this algorithm will be very bad. So in the end, you will stuck some very bad area and you will expect very bad training error and validation error and so on. So to resolve this issue, there are two type of approaches possible. The first one is some trick on your gradient descent update like ADAM or ADAGRAD or RMS probe and so on, so that you can concatenate and you can cancel out some oscillations. And the second approach is reshaping your loss function contour or loss function landscape, and that is new architecture of your neural network. So RegNet structure is one very nice example which can reshape your loss function shape more smooth and more easy to optimize using gradient descent. So after using RegNet, we can stack more layers and we can get much better training result and test performance. So we will discuss what is RegNet maybe 2 weeks later. Okay. And one another very nice technique is batch normalization. Batch normalization introduces some normalization operation for each layer, which can make the loss function shape more smooth, and which can make your algorithm converge more fast and more nicely. Because which the batch normalization normalize each layer so that it has zero mean and unit variance, which can make your gradient also every layer having similar range of values. Okay, so this kind of very ugly shape of loss function contour essentially comes from different value range of each layer. But when you arrange or when you fix this non-balanced the range of your layers, you can expect much smooth loss shape, and you can expect much better convergence behavior of your gradient descent rule.